All right. Question.
Well, I have a couple questions actually. So
Yay.
for the homework, our circuit we have for our inputs, we've got the two in-losses with their gates.
Believe it or not, I don't remember the homework, so can you tell me which problem?
Well, go to your chapter 24 because it's the same schematic we use for all of these.
Oh, okay, good. This one?
That one.
Yep, so it's a split length device, so it's you treat it as a single MOSFET where you sum the lengths.
So when we do our the CMR calculations and all that stuff, it's still gonna just be like VDD minus VSG minus.
It's exactly the same as everything you've done. All I've done there is instead of using a 50 by 2, using 50 by 1 split, so I can do the compensation and get the current injected through here. You can't see when I point with my finger. So these transistors behave as a single device. Remember, that's a problem from chapter 6, and we use that also as the load.
So for one of them, we had to compare the gain. So we had to compare the gain and everything from figure 24.3 in the book.
Yep.
To the one for this one.
Yep, it's the same.
I got it minus higher on this.
When you simulated, but when you hand calculated, it was the same. It's got to be the same, right? It's the same circuit. Yeah, I mean, there might be small variations in the split length devices, but it's the same, yeah. Should be the same in the hand calculation. All right, any other questions on homework?
VP and VM is tied together, so how we get it set it up, set of the offset stuff?
I don't understand the question.
It's asking us to plot offset when increasing the length.
Okay, how do we quickly find offset? I went over this last time.
Yeah, changing the.
No, you put the op amp in this configuration. Say VDD over 2, whatever. And then this is V out is equal to VDD over 2 plus VOS. Now you could argue that's not entirely VOS. A component of it will be the finite gain of the op amp. But generally that's small in a real op amp because the offset is due to mismatches in the input diff pair. So what's the two potential? Are they the same, roughly?
Almost, but
Yeah.
not really.
Yeah.
But the one you just posted, the homework,
Yeah.
say for the terminal and negative terminal, they tied together. The question number 1.
Yep.
Because that seems now we can't do that one. Now how are we going to deal with it?
Figure A24.1, the out will move towards either VDD because of the systematic offset. Let me look at A24.1. Oh.
Yes, that's right.
Oh. Yeah, so in this one, this is just showing that because there's a difference or an offset here, it don't work. In fact, it even says problems. Because you have a tiny offset on, you model it as being in series with the positive input, and it causes this to go either to VDD or ground. So the point of this is it does not work, and you can't get the output to go to VCM because the offset will be multiplied by the gain of the op amp and cause the output to go to VDD or ground. Yeah, it doesn't work. That's the point. It even says problems with doing this. That's why I said if you want to actually get the offset, you have to use this circuit. Other questions? Yes.
Okay.
I'm really hoping someone starts asking project questions. So.
Yeah,
Okay, thank you.
Okay, so for like simulating, because our output swing is based on our CMR, right? Mainly of like the diff amp, because that controls our input and therefore also our output.
Yep.
How do we like sim what exactly our CMR range is for that. Do we just do a sweep of like the input?
Okay, so this, when you look at this, the output swing should be 80% of VDD. So let me ask you this. Is there any way with a PMOS or an NMOS, this is going to blow your mind, so is there any way with a PMOS or an NMOS that you can get an output swing that is 0.5 to 4.5?
And that's killing me.
Yeah, you got to use two diff amps in parallel so that one turns on, the other shuts off, and vice versa. Yeah. So let's look at that in the chapter that you're reading.
I was trying to think of that too. I was like, well, based upon our, VGS and VDS data, I was like, there's no
Well,
way we
wait,
can
let's
get that.
discuss it further. So which topology is everybody focusing on?
Well,
I mean, what's the one that you're using? Let me guess, the one I went over in class. No? Oh, good. Yeah, two-stage, but I had a class AB last time.
yeah.
This thing, right? What's that? Something like this, right? And we did the Sims last time. Okay, so now no one's using this here. Let's pull up the Sim. Where did I call it? 24. Oh, right here. Let's just pick, I don't know, this one. That's the topology, right? No one's using this? Okay. So let's discuss how, well, okay, so let's stare at this for a moment and then we'll modify it. So if I don't give the wide output swing 0.5 to 4.5 or 80% of VDD, then the problem's really simple. I mean, you could probably meet the specs with this topology by itself. So I need to make it a little bit more challenging for you so you feel like you're getting your money's worth. And so if I look at this topology, just using the parameters from table 9.2, what's the minimum output swing and why? Yeah, so it can go to VGS plus 2 VDS SAT, which is roughly,
About 450.
yeah, about 450, close enough, right? So that's not going to get you to 80% of VDD. Does everybody see that?
Right.
So what I'm going to do is I'm going to put, but if I go the other way, how far up can I go?
You can go to VDD minus GSG.
Well, wait. This node is at VGS, or VDD minus VSG, right?
Yeah.
So this node can go up to that node and beyond it by a threshold voltage. So that means this node can basically go up to VDD minus VSD SAT. Does that get you close to 80% in that direction? Yeah. So the NMOS meets the specs for going positive, but doesn't meet the specs for going negative. So in this problem, when I run this, this is a 1 volt VDD. There I'm doing the small signal. Let's go ahead and close this and I'll resave it. Let's do file, save as, and let's call it version 3. Let's go change this. What's 80% of VDD then? Yeah, 200 to 800, right? Okay, so let's see what happens. You see there, the output's not going all the way down because the NMOS, well, you tell me, why isn't it going all the way down?
Because I can't go below the.
Yeah, because the NMOS diff amp shuts off. Does everybody see that? Anybody not follow this? Any questions? I don't want this to be magic. You're designing a real op amp. I want you to know what the limitations are.
So, just to make sure that I'm doing my stuff right, what we want is when we do like this, then we want our V output to be shadowing, the exact same to match.
Yes.
AP, right?
Yep, but now when
It's
this...
not 80% of that. It's 80%.
No, you need it to match. You need the output to swing from 20% of VDD, in this case 200 millivolts, to 80% of VDD, in this case 800 millivolts, but you want to actually show it goes beyond that to show that it has margin. You don't want to just design, because if you turn it in and say, hey, see, it works for exactly what your spec is, you'll lose points, because you don't design for things to work right to spec, you design them to work beyond spec. Does everybody see that?
So would it make sense to do it like your thing from 0 to 5 volts, and then your output running 80% of
Your input's what you want the output. See, the input here, let's make sure we understand. You might ask, why do we need this op amp? What does it do? Okay, this load that I have here, which is an ideal voltage source, doesn't take any, when you drive the op amp, it takes zero current, right? So if your source had a high impedance, it could drive the op amp and then drive the load. The op amp would drive the load. Does everybody follow that? So if I put a 100K resistor here in series, I would get the same waveform across the output. However, if I connected the source with the 100K resistor directly to the load, it wouldn't. It would attenuate it by a factor of 11. Plus there would be an RC time constant. I don't have that issue here when I put the buffer in. Okay, now, the problem is when I do this circuit, when I put it in there, and you know what, let me not be lazy. Let's do this so you can upload this. Projects are where you get things you can put on your resume, and if you put them on your resume and you go interview, you need to be able to discuss them, and I want you to be able to discuss them. I want you to have a good project, so I want you to understand the trade-offs here. So let's go put these in why did I delete that? I'm the king of deleting stuff. Extract here. Okay. So let's go put it in here, paste. And then let me make sure that I can still pull this up. And it works. Yay. Alright, so then I'll upload this when we're done. Whatever. Alright, so we'll make sure that you have these up there so that you know what's going on. Of course, you're in a different process. So let's go version 4. Okay, and I'm going to redraw this schematic a little bit. Does everybody understand that I need to somehow put a PMOS diff pair in here to sum with the NMOS? Is everybody clear on that? So I'm going to redraw the schematic, but when I first redraw it, it's going to be exactly what I have right now. Okay? So I'm going to go get my little hand here. I'm going to move this out of the way for now, okay? Then I'm going to move this stuff over to the right. Move this down like this. Then I'm going to come back here. And I'm going to move this over. And I'm going to move it This little screen's a killer, isn't it? Let's do the following. Let's move this here. Then let's move this over even more. Let's move this right here. And now what I'm going to do, and let's move this out of the way. Okay, so before I go any further, would everybody agree that this is exactly the same thing that we just had? In fact, let's sim it just to make sure. Let's see, there's my source, there's my output, look the same? Okay, so now, what I'm going to do is the following. I'm going to add a PMOS diff pair in there, and I'm going to sum the currents from the PMOS diff pair with the currents from the NMOS. And notice these are twice the size. Okay, I'm going to go ahead and now take my PMOS. I'm going to go copy. I'm going to come over here, plop this down, and then I'm going to, and let's zoom in on here so it's not straining your eyes. And I'm going to go change these to m equal 2, which I could do here with 2.5 and m equal 2. But we'll do this differently. And then what should I connect these to? You know, all I can think of is right now, you know, if I was on the chalkboard, I could be drawing this and discussing it, not really showing them, and that would be nice. Just check back in 20 years. I'll never get to that point. That's why it really bothers me to come in late, because it's a slippery slope. You start letting something happen, and then it just keeps getting worse and worse and worse, you know. And it's been worse it's been bad this semester, so even doing my best. All right, everybody cool with what I did there? Okay, so what I'm going to do now is I'm going to go grab everybody knows what I mean by a slippery slope, right? You start doing something, and then you start doing it more and more and more. Okay, I'm going to go grab this, and then I'm going to put this in here, and then I'm going to come over here and copy, and then I'm going to drag this, and I'm going to pull it, and I'm going to Control E it. And now I'm going to come up here, come over and go down. I'm going to come here. Now, does everybody see I need to sum the currents from this diff pair with the currents from this diff pair? So let me think for a second. The way I'm going to do that is the following. I'm going to take and I'm going to copy these. And I'm going to move these over here like this. And I could actually get away with a simple diff amp, but you know what, I'm going to draw it a little bit different. Before I do that, let me label this V bias 3. And then let me come over here. And let me think about this for a sec. Got to make sure I do it right. And then I'm going to come and bring this over here. come down here. Let me just pause for a moment. I'll explain what I'm doing here in a second. I got to make sure everything biases up right. I'm going to get rid of the scissors here. I'm going to get the scissors there. I'm going to go over here. And I'm going to copy this down here. Call this V bias 4. Now, if I look at this, you say to me, wait a sec, you have a current source here and a current source here fighting. That don't work. So I've got to be able to create some imbalance in there. So the way I'm going to create the imbalance is the following. I'm going to connect this one over here. Connect this down here. I'm going to do this several ways, and I'm going to explain it so you understand what's happening. And then I come over here. So let me ask you this. Let's just say our bias current, what is it for the 50 nanometer table 9.2? How many microamps? 10. So I get 20 flowing through here, 10 through here, 10 through here. Now, if this amplifier shuts off, this one's going to continue pulling 10. This one will pull 10, but there's 0 current left to pull through here, right? So I look at the water flow. Got 20 flowing through here, 10 through there, 10 through there. If I bias this with these sizes, then the 10 goes through there and the 10 goes through there. There's nothing left to flow up here and these shut off. Does everybody follow that?
So they just kind of like swap.
Yeah, so let's say that I'm biasing up and both of these are right at VDD over 2, so both the NMOS and the PMOS diff pair are on. Does everybody follow that? So I've got 10 flowing through here, coming in, going down through here, 10 flowing through here. Remember, these are, here, let's be consistent. Let's call these 2.5 and 2. And just to be consistent with the other, 2.5 and 2. Does everybody follow that? And so I've got 10 flowing through here, 10 flowing through here, then flowing through here. I got 10 and 10. Everybody's happy. But wait, if I output goes to 200 millivolts, we just saw this NMOS shuts off. So these shut off as well. And the only current that flows is through here.
If that NMOS shuts off,
If this diff pair shuts off, there's no current flowing through here.
but won't that turn those on?
Turn what on?
The PMOSes?
These?
Because it's connected to the gates?
No, they're off. So how much, if they're off, how much current flows in here? Nothing. So they're out of my mind. Here, what I have is I have a current flowing down through here. This is a current source of 10. This is a current source of 10. And I've got 10 flowing through here. But this node, which clamps this node at VDD over 2, doesn't have any place to flow, right? I mean, there's no reason for this to turn on, so it can shut off. You follow me? Okay, so it's very simple. If I have 10 flowing through here, 10 flowing through here, 10 flowing through here, 10 flowing through here, where, if there's, you claim there's current flowing through here, where does it flow? There's no place for it to flow. 10 through here, 10 through here, 10 through here, 10 through here, current flowing in this wire is 0, because there's nothing coming out of here. So to fix that, what I'm going to do, I'm going to make these twice as wide. Does that make sense?
So then that creates excess current that these flaps out.
That creates excess current. No, that just means that if these shut off over here, there'll still be some current that can flow over here. You know, I'm going to make this simpler so we don't have, because it doesn't matter. Let's get rid of these. Let's go ahead and put from here down, yes.
So even though the NMOSs are turned off, just by widening up the PMOS, there is going to be room for that current to flow because of the widening.
Whoops.
Correct?
You know what? Wasn't this wire supposed to be labeled? Or did I delete the label? Oh, no.
No, it's time.
Okay. Yeah. So what I'm trying to do is make sure that it does have a current flowing through it. And the problem with this is, and there are issues which I'm going to fix in a moment, is that it's still going to have problems. So to answer your question, even though I double that, there's still going to be issues. Okay? But I want to show those, and I want to come back to this, and I want to show you how to fix it. Okay? So, but I want to go through and see what it looks like now. So before I do that, let's figure out what's what. If I increase this let's say I decrease this terminal, what happens here? This turns on, causes this node to do what? Go higher, which causes this one to turn off, which causes this to go down. So is this node my positive? So I've started out with this going negative. That's my positive node. So I'm going to go ahead and label it VP. So these are tied together. And then I'll go ahead and label this. Yeah, I'm just going to go short it together here. I don't want to do that. I want to make sure it's more noticeable that it's... Okay, so now I want to show you problems, and then I want to fix the biasing. Before I do that, let me show you one other problem here. If I've got this structure here, and I've got this structure here, which I could basically put in the middle here, why do I need this branch? Why don't I take these two devices, put it over here, and just move everything and just get rid of these two? Does everybody see that? It's wasteful. I don't really need this two transistors and these two. I needed them before because I didn't have the ones on the bottom. Now I don't need it. I can take these two and put them over here, take these and put them over adjacent, and simplify the circuitry. Okay? Questions? Okay, so my mind, here's what's going on in my mind. They don't understand how this is working, so I'm going to show you there's problems, then I'm going to go through on paper and show you how it works. And we're going to take a structure called the folded cascode structure, which is introduce folded cascode, and we're going to go through how that works. And then I'm going to show you the biasing and show you all the issues here. But keep in mind what we have here. Is this a cascode, by the way? No, it's a split length device. But if I replace these with a cascode and these with a cascode, I can actually get higher gain, and that's all make my 1%. So let's go show this doesn't work. Okay, it still has issues, right? Does everybody see that? Still not behaving correctly, and it's because we have some issues here with pinning this node a little too close to VDD. Does everybody see that? This node is VDD minus a VSG, so this guy can actually shut off because its drain is a little too high. Questions? Okay, so I don't expect you to understand all the finer workings. All I expect you to know is there's problems and we want to look at how to fix them. Okay, one more time. Any questions?
I didn't exactly understand the wasteful part. You said we don't need those.
Okay, so you see these two transistors are exactly like these two.
Right.
These two we could replace with a single current if we didn't have it, so that we could put these in the middle here with this. In other words, we move this, 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 and this over here and get rid of these four.
Okay.
Okay, we'll do that hopefully today, but maybe next time. Okay?
You're saying it's just redundant. Well, really, they're not really they serve no purpose.
They serve no
As far as
purpose.
As far as the way that they're wired,
Yeah,
they
they're
serve no
just,
purpose.
yeah, they don't do
So
anything.
the ones that are to the right,
Yeah,
those are the ones that should be
Yep.
in the middle.
yep, exactly. Okay, so let me just make sure one other point was clear here before we move on. Did everybody notice the response looks pretty similar to what we had without the additional stuff? And I want to make sure everybody understands why. Let's see if I can delete the yay. This node here is fixed at VDD minus VSG. If I go through, that's not what I want this to be. I want it to be able to go lower. And if I pin this node at VDD minus VSG, it's not going to take much to shut this off. So if I go look at the current through this device in the simulation, and you'll have it, you can do it later, that's going to show that it's not wide, we're not getting wide swing operation. This guy can't stay in saturation because its drain is at VDD minus VSD. So I need to fix that. That's the bottom line. And we will fix that right now. Okay? But enough simulation. Let's do the following. I need the drains to be able to swing. And I need to be able to inject currents. So here's what I'm going to do. And I'm going to do this for the PMOS flavor instead of the NMOS flavor to begin with. So I'm going to put a structure that looks like this. And then I'm going to come down here. Okay, so this is a cascode structure, everybody would agree, right? So I'm going to come down here. And I'm going to diode connect this and connect this to V bias 3. Then I'm going to come over here and I'm going to run this out. I'm not going to put the output buffer on for the beginning. I just want to explain the operation. I'm going to call this V out. Then what I'm going to do, in order for it to bias up correctly, I'm going to make these all times 2 as well. So according to table 9.2, I have 20 microamps there, 10 there, 10 there. Flowing in here I have 20. Flowing in here I have 10. Whoops, I have a mistake. And flowing in here I have, these should be times 2.
Just the bottom.
Just the bottom. I'm going to change this in a moment. Does everybody follow that? Okay, so let's see which one's the positive and which one's the negative input. So if this terminal, let's change colors. This terminal goes up, what does it do to this device? Off. And if it has less current, and I've made these bigger, what happens to the current flowing in here? It goes down, so this essentially sinks less current, so the current goes down. I have to shut my phone off. It would be rude of me to take this call, wouldn't it? I'm sure none of your professors have ever done that. What's that? Actually, you know. What? Oops. Well, if it's a matter of life and death or something, I could see if you're dealing with family issues, but then I would try to say beforehand, I'm expecting I have some urgent medical, just like you would if you needed to take the call, right? I'm gonna have to step out, I have a call. It's polite, right? Okay, or you would apologize as you're leaving and say, I should have told you I'm expecting. Anyway. Damaged.
We're having a manners lesson.
Yeah, so anyway, what does the output do then? If this starts to decrease, less current, then all the current that's flowing in here doesn't have to flow down here, so what happens? It goes up. So this is the positive terminal and this is the negative terminal. Let me simulate this before we go on, all right? And question?
Only the, so basically you're doubling the size of the PMOS on the top left.
Yeah, so just, I want to make sure you know that I'm not pulling things out that you haven't seen already. So let's, here, just, and I'll be in this weekend, although we'll have to arrange a good time because I've got so much work to do. 7:30 in the morning? Don't tempt me because I started working this morning at 5:30, so.
Straight from work, I'll be here.
All right. Well, maybe it would be good to do it later because then you could get some rest and
Computer lab does no.
you know your perspective on life is much better when you're rested, right? Yes. So does everybody see this is the NMOS equivalent? This is my times 2. Here's my times 2 here, and then this is the folded cascode. Here's my diode connected. So I'm doing the PMOS just to be a little bit different, but this is the NMOS equivalent. Is everybody cool with that? So this is the exact same circuit that I'm going over right now, except it is the NMOS equivalent of the circuit.
Oh, that's like your.
So here's the 2 in parallel. There's my PMOS. This is figure 2442. Okay, and then there's my bias, etc. So if you don't understand me, I'm like, his lectures suck, I don't like them, I want to read the book, then you can go back and read the book. Okay? All right. What do you know? No message. What a surprise. All right. Yeah. You know, because of my website, Google's trying to get me to do advertising. They call me like daily and they try to rotate the, yeah.
800 numbers?
They try to rotate, yeah, no, they're not 800 numbers. They're various ones. Like sometimes it's Maryland, sometimes it's Virginia, sometimes it's Oregon.
It's like Red Cross.
Yeah, yeah. Well, I used to give to Red Cross, but you all know about my little episode. Was not good times. All right.
We're gonna watch the video this afternoon. There's gonna be an ad before.
Yeah. Okay, so let me simulate this and then I want to derive the gain. Actually, let's derive the gain right now real quick. So what do I put here for the effective output resistance? Okay. And now I look at this, and let's say that I have a current that flows here. Let's just say it's flowing in this direction. I call it GMP times Vn over 2. And I have a current flowing in this direction, which is GMP times Vn over 2. The total current flowing into this node is then GMP times Vn. And so V out over Vn equals GMP times R out cascode N in parallel with R out cascode P. And I want to drive that yet again. I mean, you just had a quiz on diff amp operation, right? Okay, so let's go look at it. So how many stages is this? It's a one stage because these are low impedance nodes because of the sources here, the drains. And so there's one high impedance node, which is this one. And so a circuit with only 2 high impedance nodes, the inputs and the output, is called an operational transconductance amplifier. And the reason we like those is because they're easy to compensate with a load capacitor. And I'm going to show you that right now. Okay, just before I go any further, What's the maximum input common mode range?
VDD minus 2 VSD sat.
Yay. VDD minus 2 VSD sat minus VSG. It's not very high, right? But this is at VSD sat. So these can go to below ground and they'll still be functioning right. Unfortunately, the output's limited to 2 VSD sat, VDS sat. So about 100 millivolts. So even though I put it in the follower, I can't go negative with these because the output can't swing negative because I need 2 VDS sat. Yay? So I want to take the schematic we just had and I want to modify it and show you how this works. All right. And because we're running late, because somebody started late, let me go ahead and axe a bunch of stuff here. Ugh. Let's stretch this over. And let's move this here. Here. Move this here. And let's stretch it over a little bit more. And then let's go ahead, and I don't want these to be, let's move this out of the way. This can only drive high impedance loads, so I'm going to replace this capacitor here. And let's move it over. Hit fit. And then let's move this a little bit more even. And then we need to get the scissors out. And then this is going to be labeled V bias 1, V bias 2. Get the scissors right there. And then let's go ahead and get rid of that. And then let's copy these. Let's move them right here. It's good times. Let's move this here. And then let's make these two m equal 2. Does everybody see what I'm doing? And then I got to do one other fundamental thing, which is, okay, I got to do that. I was thinking even more fundamental than that. Well, what about these two connections here, right? They don't go here. They want to be pinned at VDS sat.
Oh,
So why don't we do the following? Actually, let's do it this way. Oh, it's kind of tight, but we'll get it to work. Ugh. And does that look like our circuit? M equal 2? Oh, I don't want those to be M equal 2, do I? I don't want either of these to be M equal 2. What's that?
Yeah, the bottom two, right?
Yeah, just the bottom two.
Top.
These aren't, these are. Okay. And then what do I need to show?
Yeah.
Yeah, I need to connect V out, but let's not go all the way to, let's see, our maximum output's probably about 600, I would guess. Yeah, let's go a little lower just to show how stability. And then let's go connect this around. Notice if we did this with a diff amp in the 50 nanometer process, it wouldn't be that good because the diff amp has low gain for 50 nanometer, but we're doing folded cascode, so it should be pretty tight. I mean, the gain output should follow the input pretty well. Okay, any questions on what I did there? Does everybody follow the flow of water? You got 20 flowing here, 10, 10, 20 in these, and then I've got these as constant current sources.
Question.
Yes?
I'm looking at the figure for this on similar page 715, and it has the full cascade amplifier.
715. Back in, yep.
This is kind of what I was using, what I'm using mine.
Good.
I was curious, has the V plus gone to the other side and V minus on the other?
Because I might have made a mistake. V plus. Oh, no, I didn't. That's the same. Yeah, V plus is on the right.
No.
Oh, I flipped the wires.
Yeah.
I probably made a mistake. It's easier just to, I'm sure the book's right. The book's always right. Let's fix that. Well, let's make sure that it's right before I do that by talking it through. So let's see. If this goes up, that shuts this off, which allows more current to flow through here, turns this on, pulls, yeah, that's right. I must have talked myself wrong last time. All right. We ready? Questions? Roll them. So let's see VP. Let's see. Looking good. Nice and smooth.
So say if we went from like 100 millivolts to like,
Let's hit run. Oh yeah, that's fast. Does everybody see that? And I see I've got a little bit of a issue with the diff pair not pulling it up. So you want to go 100 millivolts to what?
like 900?
Let's do it.
Because our output swing is 80%, right? So then that would be an 800.
Let's do it. 200, or what did you say, 100?
100.
To 900? So that's 90%. Let's go 150 just to give us some margin to 850 and see that it fails. And then we'll fix it. It's actually not horrible.
Pretty close.
Yeah, I mean, but it's not pulling it up right, and this isn't coming down all the way. So I want to fix this and get wide swing operation by adding the NMOS diff pair in. But before I do, are there any questions? So where is it discussed in the book about putting PMOS and NMOS diff amps in parallel? Now it's discussed in chapter 22 and in chapter 24. Let's see where in chapter 22, like in pages 738. Okay, so since we're running out of time, as usual, because someone started late, let's go ahead and do this, and you're going to tell me what to do. Whoops. Tell me how to modify this so that I get good behavior.
Like so it'll go up higher?
Yeah, so I get full wide swing operation. Okay, so we'll add the NMOS. I'm gonna, because I want to plant subliminally some, yeah. I'm gonna modify the schematic in a little bit neater way. So I'm gonna take this stuff and yank it over. All right, and let's go ahead and, oops. You know, I wonder, why can't it read my mind on what I want to do? All right. Tell me what to do. Here, let's do the easy part first. Let's go open the previous schematic, which was this one. And then let's grab this stuff. Ugh. Trying to make it look pretty. Okay, so where do I want this terminal be connected to? Do I want it to be connected here? Say again. So if this goes up, what do I want? I want my output to go up, so I'm going to connect it to this side to steal current, or whoops, I'm sorry, to this side to steal current from here so that it allows this to shut off. So if I pull this up here and I go over, when I steal current from here, that means there's going to be less current flowing down here. This is going to shut off. When it shuts off, this is going to shut off and allow my output to go high. Does everybody agree with that? Then I'm going to connect this up over here like this, but now what's the deal?
Like C1
No, with the biasing.
you have to make those top two
Wider,
wider,
right?
right?
Okay, so now let's think about that for a second. If I do that, what happens when, say, the NMOS diff amp shuts off?
Then it would
Force twice as much current through each side, right? But I've got a diode connected device here. It'll just adjust to sink that extra current. So I'm going to get a different gain depending on the input common mode range. If the input common mode range is so that the NMOS diff pair is off, I'm going to get one gain, say 1,000. Then if both are on, I might get a gain of 2,000 because the GMs are in parallel. And if only the PMOS is on, then I might get 1,000 again. So the gain's going to vary, but you say, who cares? That's the whole point of using feedback, is I can tolerate bad gain, or I can tolerate changing gain. Does that make sense, Dane?
For the most part.
We'll see. See if it works. When you simulate it, we'll see. So let's go up here. Go 2. 2. Hit save. I think I overwrote the previous one. Oh well. Oops, something's not right. Let me see what's happening.
I think you need to swap your PMS channel.
The what?
You swap your input to the opposite ones that PMS is connected to.
You think so? I don't think so. I think this is right. Here, let me look in the book. So my PMOS go there. That one goes to the right. That one goes to the right, that one goes to the left. Should work. Do I have any size issues? Huh. Let's look at what's going on here. Okay, goes to 0. That makes sense. That goes to 0. That makes sense. Whoa, something's wrong. Why is there so much current flowing in there? M equal 2, M equal 2. So you see what I did, right? I just said, okay, what's the current flowing in there? When the input's at 100 millivolts, it should be 0, but then it should, oh, okay, that's reasonable. But up here, when I look at the current, when it goes to 900, 850, it should go to 0, but in the other cases, it should go to 10, and it's not. It's going to 45, so I got a biasing problem. Help me find it.
Does that bottom set need to be connected to the bias source?
Wait, that's right. No, it's diode connected. Where? This one? Nope. 50? Oh, I see the issue. Damn. Ugh. See, in Cadence you can select all of them and just change it all at once. All these are messed up in the biasing, because in the bias source, in table 9.2, I use 100 nanometers, right? So the biasing's all boogered up. See what happens when you copy. Alright, you see any other issues? Whoops. Alright, there we go. Looking better? Looks nice. Now notice there's this little issue with it going not all the way to VDD and not all the way to ground. You won't have that, because what are you going to do? When you do your designs, what's going to be different? This is a one-stage operational transconductance amplifier. You're going to have 2 stages, so your output's an inverter. So it's going to be able to swing from VDD minus VSD sat to VDS sat. This one we have limitation of 2 VDS sat, and so it starts to the gain starts to drop and it doesn't pull it up. So I want to quickly, we'll see how far we can get. I want to add the output buffer, but before I do, are there any questions? We'll see how fast I can do it, and then we'll pick up with this next time. So first thing I'm going to do, notice what happens when I add the output buffer. The output buffer is inverting, and this you probably will make a mistake when you're doing your projects, at least I would. If you don't notice that the output buffer is inverting and you go ahead and try to do your design, you're going to constantly, it's not going to bias up right because you're going to have positive feedback. So you need to switch the plus and minus terminals. So when I do this now, the way I have this set up, I need to come over here and I need to put this like that. Then I need to copy, or I need to move the VP. And then I need to connect it up like this. Does everybody see that? Then I need to add my, what do I add here? Floating current source in the middle, right? And this is half the size, so it's 2.5. Okay. And then I come over here one more time. Boom, half the size. 1.25. Okay, now I'm going to wire everything up. And then we call, what do we call those two labels? Whoops, shoot. What are those labels? And last but not least, I'm going to throw on the, I'm going to leave m equal 2 here. Oops. Does everybody see that? Ugh. Yeah, I'm going to be sloppy. Now, this isn't like, what's he doing, right? You've seen this. Then we'll go here. Looking good. Notice these are m equal 2. You can adjust the size to drive your load. We'll hit save. Oh,
You guys look at that
VP.
the bottom end loss on your amplifier, to the left, down.
Oh, okay. Thank you. And then what else do I need to do? Connect the output around. And then what else do I need that's important? Yep. So I need a compensation capacitor. Where am I going to put it? Yeah, right here is good enough for now. Let's just throw in a value of 200 femto. And then let's see what happens. Since we didn't look at anything, we're just saying, hey, let's see if we can get it. Because if we don't put that in, it'll ring like crazy when we run the sim. Whoops, something's wrong. It's not letting me select the... V out. Do I have something labeled twice? There's VP. I have this labeled VP, I think. Wait, highlight net. Okay, where else? Oh, right there. See what I did there? It's a little trick. So you waste a lot of time if you do that. Hit run. All right. Yeah, it's not too bad for doing nothing. You can see there's a little instability. Let's quit here. When we come back, I'll go through this in more detail. Any last second questions?
I'm using minimum stuff a bit for the analyst, and I can't really use that last stage, can I?
You have to be able to split, but there is no split links in the folded Cascode.
No, I mean, in the output where you split the width, if I'm using the minimum width, you went to 1.25.
No, you just divide W by 2, not L.
Using the minimum, it says the minimum is 3 micro.
Then you multiply L times 2. Right?